So we have a total of about 80 grams there. Well, when this is by itself, we have 500 grams, but when we submerge it in water, we only increase our mass in there by 80 grams. We don't have the total 500 grams. Well, the reason why is, well, what occurs here? Well, we have an apparent weight. Weight of the object is submerged in fluid. It's not going to weigh as much. And the reason why is why doesn't it weigh as much? Because of buoyancy. So we have what is called a buoyant force. And that buoyant force is a net upward force exerted on an immersed object. It's the net upward force that is exerted on the object. Buoyant force is not, this goes to a different aspect. You have something that's helping you lift up. You want to think of it that way. Something is helping you lift up. It is not visible to you, but it's like a magic field that's sitting there saying, oh, rather than having 500 grams there, I only have 80 grams. 80 times 9.81, rather than having 500 grams times 9.81, I only have 80 grams times 9.81. I have less of a force that I have to exert to lift something up. We have a net upward force exerted on the object. Makes things a lot easier. When we deal with objects that are immersed, when you feel that pressure on your head or on your eardrums in the water, that is the weight of the water above you that's pushing down on you. Okay? So when you're sitting in a pool or you're sitting on the bottom of a 10-foot pool or 8-foot pool and you're sitting there on the bottom, you feel this pressure on your ears. What you have is you have all that water on top of you that's pushing down on top of you because water has weight. That water that is there has a weight to it. It has a mass that's above you. That gravity is pulling down in that weight and putting it onto your head and into your eardrums. So what you're feeling when you're working with water and sitting in the bottom of the pool or sitting something in water, whatever that water is above you is pushing down on top of you. Why? Because gravity is pulling it down. You have removed the space of some water by your volume. You have a volume. When you jump into a pool, the water level will rise a little bit. Okay? Won't be much because it's a little bit bigger. But if you would put 20 of your friends in a pool, okay? If you have a pool and you put 20 of your friends in that pool, if you have an above ground round pool, water is going to start splashing out of it. Or if you have an in-ground pool, if you look at your gutters in the in-ground pool, you have the squares there. If you put 20 in your people in the pool, rather than being here with your water level, it's up a little bit higher on the gutters on the sides. Why? Because you have replaced the water in the volume of the water by your volume. Okay? So your volume is replacing the other volume of the water. That water is going to get pushed up above a little bit more, but the water that's sitting on top of you is pushing down on top of your head. Just like if you put any weight, if you put this book on your head, okay? This book is pushing down on top of me. Okay? Just like if I had a column of water that's sitting on top of me, yes, it actually balances it out. I got a flat, bald head. It works out pretty good. Okay, I don't have the muffy hair that you two guys have, where stuff bouncing that hair a little bit more up there. Okay, mine's flat and bald, so it works out a little bit better. Okay, so just like the book was pushing down on my head, that column of water that's sitting up above you, that you look up and you say, there's water up there, is pushing down on top of your head. It has weight. Okay? It has weight, so it has a directional force going downwards. Okay? So, if we take a look at pressure, pressure is equal to force divided by area. So if I take a look at this object right here, we have an object that's immersed in water. I have a force that's pushing downwards. I have this area of the top, and I'm going to keep this a very uniform area here, just to make it easy on ourselves. It's going to be a cube or a rectangular prism, where the area of the top and the area of the bottom will be the same, just to keep it simple for us. Okay? But you have a force that's being pushed downwards from this water right here. Okay? So you have a force, and you're going to divide it by this area, whatever the top surface is. So you have a rectangular shape, immersed in water. Okay, it's immersed in water. You have water that's sitting up above this that's pushing down on top of this. Okay, we have an area that's here. We have an area here. So what I can calculate is what is my pressure by taking the force and dividing it by this area right here. Because force is equal to pressure is equal to force divided by area. So what we have here is, well, this force, how do I calculate this force? Well, when I'm dealing with force, I have the weight of water. Once again, the weight of the water that's above this is your force. Okay? That's what's pushing down on your head, weight of that water. Well, how do I calculate weight? Mass times gravity. So weight is calculated as mass times gravity. So I have this mass of the water up above times gravity. So we have the mass of the water up above times gravity. That gives me a gravitational force. Am I taking notes today? What are we watching? Huh? All right. So the weight of this water is the force that's pushing down on us, times divided by gravity. Well, how do I find the mass of water? Or I'm sorry, how do I find force? Once again, the weight, mass of water times gravity. Well, if we take a look at what we talked about yesterday, or 2 days ago, how do we calculate density? Density is mass divided by volume. Density is equal to mass divided by volume. So I have mass of the water, density of water, and the volume of this water that's up above. Well, if I multiply both sides by volume, I get the mass of the water is equal to density times volume. Okay, just multiplying both sides by volume. Well, if I take a look at this volume of water, here is the volume of water we're dealing with. All this up above here. This is the volume of water. And if we look, this block is submerged in water. And if I look at the volume of water that's above us, okay, we can go a straight line here, straight line here, straight line here, straight line here. This is the volume of water that's above us. This water over here is not putting pressure on us. Okay? Because this water over here is not, and this water over here is not above us. The only thing, once again, that's putting pressure on my head is this book. It's putting pressure on my head. Things that are out here is not putting pressure on my head. Well, the atmospheric pressure is, but that's a mute point. So, if we take a look, this volume of water that's up here is the volume of water that we're talking about here. And that's our volume of water. Well, how do I calculate the volume of that shape that comes up from here, up from here? Well, what we have there is we have a rectangular prism. So we have the area of this base times the height. So we have the cylinder here. Okay, we can take the area of this base and multiply it by the height, and that will give me my volume. So the volume of this water is the area of that top times my, and I'm going to call this height 1. Okay, so this area of this top surface, and I multiply it by my height, will give me my volume of that water that's up above me. So we can now make a substitution to this, is the mass of the water is equal to the density of the water still, but the volume of this water is the area of this top surface times, well, whatever my height is of this water, H1. Because that's what's, once again, putting pressure on my head or on the top surface there. That's what's pushing down. Okay, so if we take a look here, this mass of the water and this mass of the water. If we make a substitution here, what we are left with is what I came up with here, density of the water, area of the top times the height. That is this right here. And we are substituting in for the mass of the water. And we multiply that by gravity, and we divide that by the area of the top. So that's the pressure that we feel on top. But if we take a look, we have two areas that cancel out. So these areas go away. Which will reduce us down to density of the water, H1, height 1, and gravity. That's my pressure on top. That's my pressure on top. The pressure underneath is a little bit more difficult to think about because you have water underneath. But you can follow the same idea in regards to the pressure at H2. Will be density of the water, H2 times gravity. If you would just lower the object down to the bottom there, when we get down to H2, that's going to be my pressure at H2, which is the very bottom, here. That's your H2. That's your pressures. Now, what we have to remember is force is equal to pressure times area. Okay, force is equal to pressure times area. What we want to deal with here is the sum of the forces in the y direction. we have a force 2 pushing up, and we have a force 1 pushing down. So if we just take a look at the sum of the forces, in the y direction we have force 1 plus a force 2. This force 1 is going to end up being negative because it's going downwards. Force 2 will be positive because it's going upwards. Now what we have to remember is how we deal with the forces. Well, we calculated pressure here, but we had to multiply by area of the top and area of the bottom. So we have, this is my pressure 1, or this is my P at 2, this is my P at 1, and we have to multiply by the area, because pressure is equal to, force is equal to pressure times area. What we have in common in both of these is we have in common density, gravity, and area. Once again, we're trying to keep this as simple as possible and just look at a uniform area. This will work for any areas as we go through. So if we factor this out, what we are left with is just a lot easier for you to write if I don't write it. We have density of the water, we have gravity, and we have the area, and we factor that out, we have just are left with H1, H minus H2. If we look at this quantity right here, we have area of this top times H2 minus H1. So we're subtracting, here's our H2, we subtract off H1. So we're subtracting that from the entire. What do we get when we just subtract H2 minus H1? Not the volume. Take it back a step. That's the next step. Not the area. We already have the area. I'm just looking at H2 minus H1, the height of the block. So we're getting here the height of the object. So we are looking at the area of the base times the height of the object, which is now going to give us the volume of the object. So this gives us the volume of this object then. So the net upward force and the buoyant force, if I would take the net upward, make one more substitution here. This is the sum of my forces in the y direction. We have density of the water, we have gravity, and then we have the volume of the object. This gives us our buoyant force. Which, now, you think about this, what the buoyant force is dependent on gravity, which is a constant. We have the density of whatever the fluid is, but then we have just the volume of the object. So we have density of the fluid and just the volume of the object, whatever the volume of that object is. So if you do not have a uniform block, it's okay. It still works out. You just have the volume of whatever that object is. You find this volume, whatever this volume is, you multiply density of the fluid, whatever the fluid is, times gravity. Your buoyant force is a net upward force. Now, if an object like this is submerged in the water, it's floating in the water, okay? Which means what might happen here is the buoyant force and the force of gravity will be equal. It's not, it's just stationary. But if you look at a buoyant force, this object here is submerged in the water. Is it moving side to side? Outside of me tick-tocking a little bit. No, it's not. Okay? It is not moving side to side. What happens with this immersed object is we have a force on the bottom, we have a force on the top here. We subtract those two forces, the buoyant force, we subtract those two to get our buoyant force. But if we look at our forces side by side, I'm at the same height. If I'm at the same height, I'm going to have equal pressures at that same height. If I have equal pressures at that same height, then I will have equal forces at that same height. No matter where that height is, if I go here, I have something there, one on each side. That's giving me forces on each side. So I have equilibrium horizontally. Okay, we have equilibrium horizontally, but vertically we don't have equilibrium. Okay, we have a buoyant force up, we have a top force going downwards. Now, if something is just immersed in there, once again, what will happen is the buoyant force will equal the force of gravity. Your force of gravity and your buoyant force will be the same. If it's just sort of floundering around in the water there, and just sitting in the middle of the water, those two will be equal. Okay? This object if I allow, would go down to the bottom. Okay? The gravitational force would be greater than the buoyant force. I still have a buoyant force, but the gravitational force will be greater. The gravitational force will be greater. Why? Because it's sunk all the way to the bottom. But if this stayed right here, that means they would be equal to each other. So you can look at basically now is in a situation here with an object in the water, with some object in the water, we have force of gravity that's pulling it downwards, and we have our buoyant force that is going upwards. So you have force of gravity and buoyant force when you have objects immersed in water that you have to worry about in the vertical direction. All right, questions? All right, QED. Please done.